In this video, we look at a momentum collision question. A 0.24 kg billiard ball is moving at 3 meters per second, strikes the bumper of a pool table. So I've drawn a sketch so that I can see the event more clearly in my head. So this ball moves with 3 meters per second and goes onto the side of the table, and then it bounces back at 2.4 meters per second. So if I then draw another arrow saying that afterwards it bounces back, and I will also put the measurements. So 3 meters per second going towards the barrier, the bumper of the table, and then 2.4 meters per second coming back. And the collision lasts 0.015 seconds, so that's our time there. I've got two velocities. I would call that the first one velocity initial, and I'll probably call the second one velocity final. And this one is our mass. Okay, just by reading this text, if you're not even reading my title, you got mass, you got velocity, you got time. So mass and velocity, that's either going to be your momentum or energy, but because they're given time, and that gives her a hint that this question is probably a momentum question, because change of momentum is force times time. Okay, so the question asks for average force exerted on the ball by the bumper. So that naturally fits our momentum calculation where we have mass, velocity, and time. Then the last thing that is not known is the force, which we can calculate. I want to talk about the common mistakes. The common mistake is to use these numbers given directly without thinking too much about the concept of a momentum. So this is what a lot of people will do. They say, okay, change of momentum is force times time, and change momentum is mv final minus mv initial. So basically it measures the change, because if you take the initial value out of the final value, you get the change. And then people will say force and put numbers in times 0.05 equals mass is 0.24 times final velocity 2.4, and then minus 0.24 is the mass times initial velocity of 3 meters per second. And look, everything is known, so calculate the right side, divide by 0.015 gives you the force, and I shall tell you this one is wrong. The reason is momentum is a vector. Momentum has direction. So when the momentum changes and when the velocity changes, the momentum also change direction. So the second velocity, if you are defining the first velocity going to the right as positive direction, then your second velocity is actually a negative velocity. Okay, so you have to put a negative sign in front of the second velocity to understand what to really be accurate about the calculation. Okay, so this one is wrong, but the correct one is f times 0.015. That's exactly the same. Final velocity is a negative velocity, so 0.24 times minus 2.4, and that subtract 0.24 times the positive 3. Okay, let's just actually put both of these in the calculator and see what's the difference. So let me move that section further down so I can actually do a calculation of the wrong one on the top. Okay, so f times 0.015 equals minus 0.144, and force therefore equals minus 0.144 and divided by 0.015, and that equals minus 9.6 newtons. And then for the second one, the correct one, let's see what's the difference. So F times 0.015 equals, both of these numbers will be negative. I'm just going to put that whole thing in the calculator. That's minus 1.296. You can see this one is much bigger than the 0.144 number, and F therefore equals minus 1.296 divided by 0.015. And that equals minus 86.4 newtons. Okay, so this wrong answer, you can see the magnitude of the force is much smaller, whereas this correct answer, the magnitude of the force is much bigger. It's especially tricky because if you use the correct definition of the change in momentum, even if you use the wrong calculation, you will get a negative force, which makes you think, okay, so this ball is going forward and it bounces back, the force is in the negative direction. So yeah, it looks like it's a correct answer, but no, actually it's not. You only calculated using the first half of this wrong calculation. What you've calculated is the force needed to slow this 3 meter per second ball down from 3 meter per second to keep going forward at a slower rate of 2.4 meter per second. So if it's slowing the ball down, you still need a negative force going the opposite direction of the ball. So yeah, that answer is only for slowing the ball down, but not to bounce the ball back. In order for the ball to bounce back, you not only need to slow it down, you need to slow it down completely to 0, and then giving it even more force to for the ball to go the opposite direction completely. That's why your second calculation has a much larger result. So the key takeaway of this question is that please remember momentum has a direction. So when you're calculating momentum using your velocity numbers, it does matter whether your velocity is positive or negative. And you have to define a positive direction once you've drawn your picture, and then call the other direction of velocity negative, even if the question has not said it's a negative 2.4 meters, because it's going in the opposite direction, it bounces straight backwards, then you have to write that velocity as negative 2.4. All right, thank you for watching.